Okay, looks like we've got a quorum, so I think we'll just get started. Great, so welcome everybody. My name is John Perkins, and thanks for tuning in to the USGS Landslides seminar. This is a meeting hosted by the USGS Landslide Hazards Program, co-organized by myself and Shelby Arendt. And we have some additional technical assistance from Jamie Kostelnik. So for those of you who are new to this meeting, you've got the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone or video camera. And so we're going to wait till the end of the presentation to take questions as we normally do. And in the meantime, please do your best to make sure that the microphone is muted when you aren't intended to speak. So it is my pleasure to introduce Colleen Murphy, who is currently a USGS Mendenhall postdoctoral fellow at the Geology, Minerals, Energy, and Geophysics Science Center office here in Moffett Field in California. Colleen received her undergrad degrees, plural, in both geophysics and geology from UC Berkeley, then ventured to UC Santa Cruz for her dissertation work on understanding the hydrology and mechanics of earth flows in the California Coast Range. And with that, I'll let you take it away, Colleen.
Thanks, John. Okay, so I want to start us off today with a simple prescription for rainfall-induced landslides. You need the right combination of sufficiently wet antecedent conditions combined with a high enough intensity of triggering rainfall. The relative importance of these two pieces might vary depending on location, but the need for both criteria to be met is particularly important in California, where we have significant variability in our climate, both seasonally and interannually. Situated on the west coast of the United States, California has a distinct landslide season, with the majority of slides occurring between December and March, as you can see illustrated in the histogram here from Cordera et al., cataloging the occurrence of landslides in the San Francisco Bay Area. And this distribution makes sense given our Mediterranean climate, where we typically have hot, dry summers, followed by cool, wet winters. And even beyond the striking seasonal variability, though, rainfall in California can also be infamously variable from year to year. So this is illustrated nicely by this map here from Dettinger et al., visualizing the coefficient of variation of annual precipitation across the country. The coefficient of variation here is measuring the range of annual precip by taking the standard deviation divided by the long-term average. So higher coefficients here indicate large fluctuations from year to year. And as you can see, California stands out like a sore thumb compared to the rest of the country. So looking forward into a future driven by climate change, this inherent variability is going to become more and more significant. And as I'll argue today, can complicate the story for how climate change might affect surface processes. So to start digging into that, what changes do we expect to see in California? Looking simply at the long-term annual precipitation, we don't actually anticipate a lot of change there. This figure from California's fourth climate assessment shows projected percent changes in annual rainfall by the end of this century relative to the last half of the 20th century. The left panel is showing projections for the RCP 4.5 scenario, and the right is showing projections for the more extreme RCP 8.5. Under this most extreme pathway, we start to get maybe some drying out in the southern part of the state, maybe things get a bit wetter in the coastal mountain ranges. Overall, the differences aren't huge. However, these averages hide maybe the most significant changes we expect in the future, which are substantial increases in our precipitation variability. So while California has long been known for both our dramatic floods and our droughts, many of you may also have become familiar in the last few years with the increasingly common term of weather whiplash, coined by researchers out of UCLA, which has become something of a shorthand for describing the increasing variability we're expecting to see in our future. As the climate changes here, we're anticipating seeing an increased frequency of both wet and dry years, as well as shorter, more intense rainy seasons, and an increased frequency of whiplash years, where we transition immediately from an extraordinary dry year to an outlandishly wet year. So we're not necessarily getting much wetter or drier on average, but the timing and intensity of how our rainfall is delivered will be changing. So how might that affect our two needed conditions, the antecedent saturation state and the triggering rainfall that are required for rainfall-induced landslides? The answer to that isn't necessarily straightforward. So first, we don't anticipate those large changes in annual rainfall in the future, but we do anticipate average temperatures will rise, and presumably evapotranspiration will rise as well as a result. Would this be enough to significantly affect our antecedent conditions? Could that dry the soil out enough to diminish or even counteract the effect of rising rainfall intensities? And on the subject of rainfall intensity, I mentioned that the rainy season is also expected to get shorter. So this could lead to a potential magnitude frequency trade-off, analogous to the question from fluvial geomorphology of which flood has the most impact on the river. It's not the biggest one, and it's not really the one that happens the most often, but a compromise somewhere in between. For our case, if we're getting more intense rainy days, but they're happening in a shorter time, does that lead to more landslides? In the extreme, if all the rain is falling in one day, we might expect fewer landslides overall. So there's only so many that can be triggered at once, and only so much water required for the triggering to occur. The rest will simply become runoff without affecting landslides overall. And then lastly, how do the interannual changes play out in all of this? We know that both extreme wet and dry years are expected to increase. So how might the prevalence of drought affect either the frequency of landslides or the conditions under which they're triggered? So which aspects of these various climate changes matter? I would suggest that the answer likely depends on the type of landslide. So we know, for example, that large, slow-moving landslides that can creep along for many years, like earth flows, are sensitive to annual precipitation changes. George Bennett and colleagues demonstrated nicely how earth flows in the northern part of California slowed dramatically in response to significant drought about a decade ago. And similarly, Al Handwerger and colleagues documented a widespread increase in velocity of these slides during the extreme wet years that followed. In contrast, we also have shallow translational slides, which tend to be sensitive to precipitation changes on much shorter timescales. We're talking minutes to hours here, assuming antecedent conditions are sufficiently wet. And substantial work was done by the USGS and others in the Bay Area during the 80s and 90s to identify intensity duration thresholds of rainfall required to trigger those kinds of slides around here. And that work continues today through monitoring efforts aimed at incorporating soil moisture data into early warning criteria. So we have two different types of landslides, sensitive to precipitation input at different timescales. And importantly for this talk today, both can be found in the San Francisco Bay Area, which allows us to investigate how climate change may affect these two types differently. And the Bay Area is an interesting place to think about in California because as you can see from this map of annual precipitation, we're in somewhat of a crossover zone in terms of typical precipitation between the drier southern regions and the particularly wet northern coast ranges. And this can have some interesting implications for how the rainfall variability impacts us that we'll get into in this talk. So today, we're going to look at two different case studies. We're going to try and model the future of landslide triggering. So the first is BALT-1, which is a hydrologic monitoring station in East Bay Hills, maintained by the USGS to aid research into shallow landslide thresholds. And the second is Oak Ridge Earthflow, a monitoring site in the Diablo Range, south of the Bay, maintained by UC Santa Cruz to study the hydrologic and mechanical conditions that can lead to persistent slow landslide movement. And I'm going to take a few minutes here to first overview the methods that we'll use for each of these sites, and then we'll talk about the sites individually. So first, our climate data. We start with an ensemble of downscaled climate projections, meaning a suite of many different models predicting what the climate might look like in the future. And importantly, large global climate projections tend to cover a very coarse resolution on the order of 100 kilometers or more, and can miss many of the details relevant for regional or local interests, such as the orographic precipitation. However, through the use of statistics and higher resolution regional climate models, and I think a little bit of magic, climate scientists are able to take these projections and downscale them to a much finer resolution on the order of 3 to 30-ish kilometers, and then you can start to capture these important local effects. And you really see that in this image here, where we have the downscaled version on the right, doing a much better job capturing realistic rainfall over the Sierra and the California coast ranges. So that's the kinds of climate data we're going to use in our workflow here. So we're going to take time series of precipitation and temperature projections from an ensemble of the downscaled climate data. We're going to input that data into a 1D hydrological model calibrated to observed conditions at each of our field sites. We use Hydrus 1D for this, which is a finite element model that numerically solves the Richards equation to simulate transient variably saturated flow. And I'll note here that this means our analysis is only looking at a point for each site and the associated temporal changes. For the scope of this project, we're not making any commentary on spatial patterns of landsliding, but we're really focusing in on the temporal changes in the groundwater dynamics. Once we have our time series of projected groundwater conditions from our Hydrus models, we identify empirical hydrological thresholds for each of our field sites that we use to identify landslides within the data. And the methods for these thresholds vary between the two sites, so I'll get into the nuances of those later on. And then lastly, we analyze our resulting projections as an ensemble in order to visualize trends across the noise. So climate models, as many of you probably know, are inherently fairly noisy, and not all models are equally as good at simulating all aspects of the climate. By looking at an ensemble of multiple different models, we can get a sense of the most likely trends that show up in the majority of the data when we look at the ensemble average, while also retaining some sense of the uncertainty by looking at the spread across all members. So we take, for example, 62 different time series of climate projections, run those through the hydrological model. We get 62 time series of saturation and pore pressure. And then we identify landslides within this data through our empirical thresholds, and we analyze the results from all 62 models in that ensemble fashion. So first up, we're going to tackle Balt 1, which is our shallow landslide site located in the East Bay. This site has been in operation since 2009 as part of the regional USGS monitoring network. Located on steep slopes, roughly 34 degrees, the vegetation is primarily grassland, you can see in these photos, and the soils are fairly shallow, on the order of a meter or so. They tend to be silty sand to silty clay, overlaying sandstone bedrock from the Orinda Formation. This site has 2 instrumentation nests, one upslope and one downslope, each containing soil moisture sensors and a basometer, so you can see illustrated in the diagram on the lower right. And I'll note the hollow containing these sensors has not failed during the monitoring period. So the data we're getting from this are not from an actual landslide itself, but the surrounding hillslopes are very prone to landslides. So here we're looking at a section of the landscape roughly 1.5 kilometers to the southeast of the site. This image is from February 2022. We don't see any particular evidence of fresh landslides here. Subsequently, in the winter of 2023, which I'm showing rainfall data for below, there was a succession of back-to-back storms that triggered mini landslides, in particular the New Year's Day storm highlighted here. After this storm tore through town, this same hillslope looked like this. So while Balt 1 itself has not experienced failure during the observation period, there are many instances of nearby landslides that can be correlated with the hydrologic observations to see what conditions are generally associated with the failure. So now let's get into the details of our model. Here I'm showing you a schematic of our hydrological model for Balt 1. The domain consists of a single column with a thickness of 5 meters, including a 75 centimeter thick upper soil layer. We use the Van Genuchten-Walm approach to define the relevant water flow parameters for each of our hydrogeologic units, and we selected these parameter values based on laboratory tests of soil samples from Balt 1 and from field measurements of hydraulic conductivity. We set the lower boundary condition in this model to allow free drainage to deeper groundwater table beneath, while the upper boundary assumes atmospheric pressure conditions with daily precipitation and potential evapotranspiration inputs. The evapotranspiration we calculated using minimum and maximum temperature projections and the Hargreaves formulation. And we account for root water uptake from grass in the upper 18 centimeters of the domain, matching our field observations using a plant water uptake stress response function. Then the last feature there, surface runoff, is generated when the precipitation inputs exceed the infiltration or saturation capacities of the domain. So using this as a base hydrologic model, we can reasonably approximate the magnitude and timing of observed pore pressures at Balt 1. As an example, I'm showing the timing from January 2023, which, as we just discussed, saw widespread landsliding throughout the region. The top plot shows the average effective saturation in the soil column over time, with the field observations shown in blue and the model calculations in orange. The middle plot shows pressure head for that same time period, and the bottom plot shows the rainfall. Unfortunately, given the restrictive nature of a 1D model, it's impossible to really fully replicate all aspects of the hydrologic conditions. So in a trade-off, we chose to optimize our soil parameters based on the pressure head time series, while ensuring that the soil saturation data, while far from perfect, did at least capture the timing of the observed changes, if not the precise magnitude. And I'll note that in addition to the results I'm showing here for 2023, this strategy does successfully capture pore pressure timing and magnitudes during landslide events in 2017, and it does not produce false positives during different modeled dry years. Now, how can we translate these time series into landslides? Analysis conducted by Brian Collins and colleagues at the USGS of the hydrologic conditions throughout the whole Balt monitoring network during 2023, in conjunction with observed landslides, indicates that landslide triggering is dependent on a combination of both positive pore water pressures and high effective saturation. And in particular, they saw that landslides started being triggered when positive pressures occurred, while the average effective saturation of all soil moisture sensors at the site is above 90%. But really, widespread conclusive landsliding occurs when positive pore pressures are reached and average effective saturation is 100%. So based on these empirical thresholds, we can identify days conducive to landsliding in our ensemble as days where the pore water pressure at the soil bedrock interface is greater than 250 millimeters and the average effective saturation in the soil column is 100%. While we can't make any direct conclusions about landslide triggering without an additional geomechanical model and higher temporal resolution, this modeling framework allows us to assess trends in the background conditions that are known to enable shallow landslides in the Bay Area. And for the sake of simplicity going forward here, I'm going to refer to the identified landslide conducive days with the assumption that they represent actual landslide events for the rest of this presentation. Now on to our future climate. So for this site, we're going to model future conditions using a 62-member ensemble of daily climate projections from the LOCA 2 dataset, which was downscaled from CMIP6 models to a 3-kilometer resolution by researchers at the Scripps Institute of Oceanography. And all models in this ensemble were selected specifically for their optimized performance over California, which is a nice benefit for us. Now, based on these data, we can see that between 1950 and 2100, both the minimum and maximum daily temperatures are supposed to increase, shown in the plots on the left. The average annual precipitation is likely to increase as well, although not by a lot, shown in this plot here. The bold line here shows the ensemble average, and the shading represents the 25th and 75th percentiles spread across all ensemble members. Meanwhile, the daily rainfall gets noticeably more intense by the end of the century. So a hotter climate, slightly wetter, more intense, how does this translate to landslides? Based on our modeling, we anticipate an increase in the number of landslide days by the end of the century, despite a decrease in the number of rainy days. So on the far left here, I'm showing data for landslide days selected with the threshold of positive pore pressures and 90% soil saturation. And remember that this is the threshold where maybe an occasional landslide starts to occur. More importantly, it's also the threshold where USGS typically issues warnings to the National Weather Service. So our x-axis here is time, and the y-axis is showing percent change in the annual number of landslide warning days per year relative to the historical average within our models. Looking at this, we see a roughly 30% increase in the number of warning days by 2100. Now, in the middle plot, we define landslide days using the more restrictive criteria of positive pore pressures and 100% saturation, which is associated with widespread regional landsliding. And here too, we see an increasing trend. And then finally, on the far right, we see a decrease in the number of rainy days, defined here as any days with non-zero precipitation. So based on these results, fewer days of the year will be seeing rain, but a larger proportion of those rainy days are likely to trigger landslides. Now let's dive into this a little bit deeper, but first I just want to make a quick note that because trends in our analyses are similar when using both the 90% and 100% saturation thresholds, I'm going to show results for the more conservative 100% threshold for the remainder of this analysis. Okay, so next up, we can think a little bit about what changes we might be expecting year to year. So on the left plot here, I'm showing you an increasing trend in the frequency of extreme landslide years across the modeling period. This is determined by applying a 31-year moving window to each ensemble member and then counting the number of days within that window that counting the number of times, in that window that the total number of annual landslide days in a year exceeds the historical 90th percentile. So we're marching forward in time. We're in 1975. We look back 15 years. How many of those years exceeded the 90th percentile? We look forward. How many of those years exceeded it? Tally it all up. Continue marching forward through time. Again, our bold line here shows the ensemble average for this count, and the shading represents the 25th and 75th percentiles across the ensemble. So to contrast this increase in frequency, on the right, we see a decreasing trend in the frequency of years with no landslides at all, suggesting that hill slopes and infrastructure are likely to be hit progressively harder and harder with fewer down years in between to allow recovery. Now, given that we said earlier on that the frequency of extremely wet years will likely increase, it makes sense that we would see an associated increase in the frequency of extreme landslide years. However, we also expect the extremely dry years to be more frequent, which to me means that decreasing frequency of years with no landslides is a little counterintuitive. I'd argue, though, as we think about it, that this is feasible if we consider that the increased rainfall intensities could hypothetically lead us to years where we have a very wet, intense December, for example, that gets us up to required soil moisture thresholds, maybe produces 1 or 2 days with a high likelihood of landslides, and then that can be followed by little to no rainfall for the rest of the winter, meaning that even with a strong head start, we can slide into the finish line at the end with only 1 landslide achieved and still well under our seasonal rainfall averages. And this interpretation is supported if we look at the characteristics of our identified landslide events. So here I'm showing you information about the rainfall leading up to each landslide event. The left plot shows the average annual rainfall intensity prior to a landslide day. So this is determined by identifying each landslide event, finding the storm associated with it, and then looking at the total precipitation and time from the start of that storm to the start of the landslide event. Our intensity is representing that total precipitation divided by the number of days it was raining leading up to that landslide. And we're seeing a statistically significant increasing trend here, suggesting that our typical landslide event is being prompted by more intense rain in 2100 than in 1950. Meanwhile, we don't see any change in the typical length of time between the start of the storm and the start of the landslide event. Although interestingly, this is one place where we do see a slight decrease in the duration if we use the 90% threshold, which I'm not showing here, but that suggests that we might reach warning status sooner in the future than we do now. And at the same time as this increasing intensity, we're seeing no change in the typical soil saturation prior to the event. So if we look at the effective saturation levels in the soil column, one day before the storm associated with the landslide begins, we're not seeing any trends in that quantity. And this is not too surprising when we dig into our evapotranspiration over this time, which shows a small increasing trend driven by the rising temperatures, but it is small. We're changing from an average about 390 millimeters per year here and across the ensemble to maybe 410 or so. So we're only adding about 20 millimeters per year of evapotranspiration. That's not much, particularly if we break it out seasonally. We see that most of that ET is not happening when the landslides typically occur. So here I'm showing daily ET throughout the water year averaged over 30-year time periods. Water year here is defined as October 1st to September 30th, as is customary in hydrologic analysis, so that we aren't splitting our wettest months across different calendar years. And the line colors are marking the different 30-year windows that we're looking at, with cooler colors as we approach 2100. So looking at this, we can see that the change is both small in magnitude, only a fraction of a millimeter per day during the peak, and the biggest changes are concentrated in the late spring, around 200 days into the water year, which is a time that typically has few landslides. So to sum up, for Vault 1, we're anticipating more days conducive to landsliding in the future, despite a slight decrease in wet days. We expect the frequency of the extreme landslide years to increase, while the frequency of years with no landslides at all decreases. And within all this, our typical landslide event by the end of the century is triggered with a slightly higher intensity than before, but no change in the antecedent soil saturation. So going back to our magic formula from the start, for the case of shallow landslides, the antecedent side doesn't really seem to change as far as we can detect. Instead, it's really about the strength of the triggering blow coming from the increasing rainfall intensity that drives the storyline. Now, how does this compare for deep, slow-moving landslides? We're going to switch gears here and dive into analysis for Oak Ridge earth flow to answer this question. Oak Ridge is a large, seasonally active earth flow, approximately 1 kilometer long, which has been moving since at least the 1930s. It's situated in the Franciscan Formation, which contains large swaths of melange, a block and matrix formation, which means it's composed of blocks of many different lithologies, anything from basalt to chert to sandstone to metamorphics, all embedded in a fine-grained, clay-rich, highly sheared matrix. And this formed during the process of subduction beneath the North American plate as material was scraped off and chewed up. And interestingly, it's actually fractal in nature, as a fun fact, with blocks ranging all the way from hundreds of meters in size to large boulders and cobbles, all the way down even to the scale of thin sections. And the weak, clayey nature of these rocks is likely an important part of why earth flows and similar landslides tend to creep slowly over many years rather than failing rapidly. In the map on the right, I'm showing you the distribution of melange throughout California, where it covers a decent part of their geologic territory, and it tends to host a disproportionately high number of earth flows. Now, locally at Oak Ridge, our geology consists of alternating bands of this melange and sandstone within the Franciscan Formation. So looking at the map of Oak Ridge earth flow here, we can see that it looks like the landslide source area is failing in melange, the gray bands on the top here, translating down over sandstone, the green bands, and the body of the landslide itself is marked in gold. And based on field observations, it's composed predominantly of melange with a few pockets of sandstone here and there. The slopes are relatively mild, about 17 degrees, and the vegetation is mostly grass interspersed with the occasional oak tree. This landslide has been monitored by Noah Finnegan's group at UC Santa Cruz since 2016, using a variety of instrumentation to get at the hydrology and movement characteristics of the slide. And during that time, we've observed a typical movement rate of somewhere between 5 and 50 centimeters per year, depending on rainfall totals. And through electrical resistivity surveys, we've been able to constrain the depth of the transport zone, which is the fastest moving section of the landslide, also where most of the instrumentation is concentrated, to approximately 8 meters. And the blue box in here is marking where most of the instrumentation is installed on the landslide. So using all of this information, we've developed a similar hydrologic model to what we discussed previously for BALT 1. Again, we're using a 1D column with precipitation input into the surface and drainage to deep groundwater out of the bottom. We aren't, however, explicitly breaking out ET this time. It's implicitly included in the calibrations. We set the depth of our landslide to be 7.5 meters here, sitting on top of a 0.5 meter shear zone. We don't have observational constraints on the shear zone thickness at Oak Ridge. This would likely be fairly thick compared to known values elsewhere. But we opted for this setup because it aids significantly in the numerical stability of our model, and it is somewhat plausible. Meanwhile, the water flow parameters were chosen to best fit the observed record of pore-water pressures following Finnegan et al. 2021. And if we look at the results, this model does an imperfect but decent job at replicating these conditions. So in the top plot on the right, we're showing observed rainfall over the monitoring period, daily rainfall in dark blue and cumulative in the light blue. And the lower plot compares the results of our hydrologic model to the pore pressure record at the 2.5 meter deep piezometer between 2017 and 2023. Observations again are in blue and the model is in orange. The purple shaded boxes here are marking the times when the sensor was not operational, just for reference. And like BALT 1, we can't perfectly replicate the complicated dynamics of this system in a simple 1D model, but in the broad strokes, we're definitely capturing timing and the magnitude of the pressure head changes over the years. Then from the landslide failure side of things, we're taking a slightly different tactic compared to our analysis at BALT 1. We know from observations at Oak Ridge that there's a consistent nonlinear relationship between the velocity and the observed pore pressure, as shown in the plot on the left. By fitting a power law to this, we can estimate the daily landslide displacement based on pore pressure values. And as you can see in the plots on the right, when we feed our modeled pore pressures through this formula, we don't do too bad. Again, orange here are modeled results, while blue are observed. The top plot is showing cumulative displacement by water year, while the bottom shows total displacement over the entire modeling and monitoring period. Again, we're not perfectly capturing the details of every year. Our model undershoots for the highest displacement year, overshoots for a couple of moderate years, but for broad strokes, the simple empirical relationship does okay, and it actually matches the total cumulative displacement quite closely. I won't be getting into the mechanical bases for this relationship today, but if you're interested in possible explanations for that, I recommend checking out a recent paper in Science Advances from Noah Finnegan and Damian Safer that ties this into rate and state friction and mechanics of slow slip. So at Oak Ridge, what do our climate forecasts say? For this analysis, we're going to use 10 models downscaled from CMIP5 data to 25-kilometer resolution by the North American Coordinated Regional Downscaling Experiment, or NA-CORDEX. This is a different, slightly older data set than what was used for BALT 1 because those newer ensembles weren't available at the time this analysis was run. Similar to BALT 1, though, we see a small increase in our projected annual rainfall by the end of the century. The bold line here, again, represents the ensemble average, while shading represents the 25th and 75th percentiles across the ensemble. And the shaded gray box is marking off the historical period, in this case, the window from 1950 to 2005. And lastly, I'll note that the data have been smoothed here with a 31-year moving window to better visualize the trend. So we see a slight projected increase in rainfall, but despite this, our displacement is projected to decrease. So what gives? How does more rainfall not lead to more displacement? There are two possible explanations for this that I'd like to put forth. First, recall that wet years are expected to get wetter, and individual precipitation events are expected to intensify. Increasing rainfall intensity during these events could cause an increase in the infiltration excess overland flow, leading to a large fraction of the rain being diverted to runoff that would otherwise have become infiltration during a less intense storm. Additionally, once the landslide becomes saturated, subsequent rainfall will run off as saturation excess overland flow, suggesting that a contracting rainy season could lead to less landslide movement over time as more of the rain becomes concentrated in a smaller fraction of the year, causing a higher proportion of it to fall on an already saturated landslide. And indeed, we do see a fairly substantial increase in the runoff out of our model over time. That being said, not all ensemble members show an increase in runoff. Some show no significant changes in the rainfall or runoff, yet the displacement still decreases. Which brings me to a second possible explanation for this overall projected decrease in displacement. And that's that we expect the frequency of both extremely wet and extremely dry years to increase in the future, and the effects of these may not be equal. So here I'm showing you frequencies plotted by counting the exceedances of the historical 80th percentile for rainfall for wet years, and the number of years with rainfall less than the 20th historical percentile for dry years. And again, we're counting up within a 31-year moving window, marching through time to get these frequencies. And so unlike in our shallow landslide case, where we can see that occasional landslides might pop up even in dry years, the prevalence of dry years might be really significant for earth flows because the system has an inherent asymmetry to it. So to expand on that, thinking geomorphically, I'm showing a schematic here of a hill slope like what we commonly see within Franciscan Melange, where thin soil caps a small weathered bedrock, a small zone of weathered bedrock, overlying deeper unweathered material. And if we're adding hypothetical landslides in here at some depth, we can create a thin, relatively impermeable layer that retains water relative to the surroundings. And then in this world, the maximum volume of water in the landslide body, and by extension, possible pore water pressure, would be constrained by the porosity and the landslide depth, barring any undrained loading effects or something else like that. That's because there's just only so much space to fill, and the rest of the water will spill out as springs and saturation overland flow. Now, we also know through in-depth hydrologic studies conducted by Jesse Hom and colleagues in the Northern California coast ranges that in the Melange, the weathering front and consequently the variably saturated zone is only about 3 meters deep, which we see at Oak Ridge generally as well. And the consequence of this is that most water table fluctuations are happening within only a few meters of the surface. But this small dynamic range can still exceed the refilling capacities of the annual rainfall. So to illustrate that as just a quick estimate, if a water table is about 2 meters below the surface, and we scale that by a porosity of 0.3, that would suggest that we need 60 centimeters of rain at an instant in time to saturate all the way up to the ground surface. However, the annual rainfall at Oak Ridge, on average, is about 56 centimeters. So this suggests that the hydrologic behavior at Oak Ridge switches from being storage limited during wet periods to precipitation limited during dry periods. In the former case, rainfall would exceed available storage, excess water gets diverted into runoff. In the latter case, if storage capacity is exceeding infiltration, the rate of incoming recharge might not be sufficient to keep up with drainage out of the landslide. And this asymmetry essentially means that while the hydrologic system can't get ahead due to an upper limit on storage, it can always fall farther behind. And whether we're coming off a precipitation limited or storage limited year really matters because we know that landslide acceleration depends strongly on saturation state. So at Oak Ridge and similar earth flows, it's frequently observed that the onset of seasonal landslide motion lags behind the start of the rainy season. In this top plot here, we're looking at model pore water pressure in kilopascals within the landslide body. The x-axis is time, and the y-axis is depth below ground surface. The colors are indicating unsaturated pressures in kilopascals, while everything that's saturated or below the water table is in white. So this plot is essentially tracking the unsaturated dynamics through time. On the bottom plot, you can see cumulative GPS displacement in green, daily rainfall in blue, and connectivity, which is a measurement of whether an incoming infiltration front reaches the water table or not, in the dashed black line. And so together, what these plots are telling us, if we go back and look at our top plot, we can look at incoming infiltration fronts in the darker blue colors here and see those propagating down. And we see that early in the season, they don't connect individually to the water table, but instead they start to agglomerate together over time, creating one big slug of a seasonal wetting front. And once this wetting front finally reaches the water table, we see an abrupt rise where connectivity is established. And after this, the landslide tends to respond to incoming infiltration events within about a day. And this is an important quirk of landslides like Oak Ridge that happens because the hydraulic conductivity is so low. And it's important because it means that the ability of any given amount of rainfall to trigger landslide movement varies temporally depending on the initial water table elevation. So in a year when drainage rates dramatically outpace incoming infiltration, may lead to an unusually low water table at the start of the following water year. In this case, more rain than usual would then be required to raise the water table back to a sufficient height to trigger landslide movement, meaning that while the landslide might receive an average or even above average amount of infiltration, a larger fraction of that occurs without triggering movement. Consequently, when a wet year follows a dry year, it might be less impactful than it otherwise would have been due to those drier antecedent conditions. And we can see this illustrated if we look at modeling from one of our individual ensemble members over a couple different years. So this plot also has a lot of information. We're going to take a minute to step through it here. First, our x-axis again is in time. And then on the top, we have daily rainfall shown in blue. Behind that, we see the cumulative infiltration and runoff over the year. Cumulative infiltration in the dotted line there, runoff in the dash. And then on the next plot down here, we're looking at snapshots of the model domain through time, just like before. Y-axis is showing us depth below ground surface. Colors are indicating modeled pressure in kilopascals. Everything in white is saturated, so the black line here is showing you the fluctuations of the water table through time. And again, you can clearly see the effect of the infiltrating rainfall changes based on the saturation state. Those darker blue spikes show points of infiltration moving into the subsurface, which slowly accumulate into one descending slug of water that then eventually meets the water table and causes that abrupt rise. These dashed lines are showing an approximation of that wetting front as it descends. Once the slug reaches the table, triggers that abrupt rise, water table responds readily to the subsequent storm inputs. Okay, and then our last two plots down here, we're showing the cumulative annual rainfall in blue, average being shown by the dashed line, and the shading is marking the 20th and 80th percentiles, and cumulative annual displacement, modeled below that, is shown in gold. Now, we can look at these dynamics over a couple years to see how both of the causes of possibly reduced displacement we've talked about play out. So our sequence begins with water year 2060, which exceeded the historical 80th percentile for rainfall. This above average rainfall was then partitioned into abundant runoff and relatively average cumulative infiltration, leading to a roughly average displacement. So this could be an example of high intensities that we're seeing there getting diverted to runoff rather than triggering landslide recharge. Then following water year 2060, we see a sequence of 4 years where annual rainfall was below the 20th percentile. And this results in a progressive drop in the average winter water table elevation and below average displacements in water year 2061 and 2062, followed by no displacement at all in 2063 and 2064. Then in water year 2065, we have above average rainfall again, but it only leads to a small amount of displacement due to the large amount of available storage that needs to be refilled due to the previous 4 consecutive dry years. In water year 2066, slightly below or decently below average rainfall then leads to mostly average displacement because we're starting with a relatively high water table previously, and our rainfall is fairly low intensity, so we're not getting a ton of runoff relative to some of these other years. And then again, we end the sequence back in a drought where we have below average rainfall and no displacement again the following year, because we end with a fairly low water table. Now, similar to this, our field observations from Oak Ridge between 2016 and 2023 cover an extraordinary range of precipitation variability, and hence they provide us an opportunity to validate the results of the modeling. Our top plot here shows rainfall observed at Oak Ridge, and the bottom plot is showing cumulative annual displacement measured with continuous GPS on the landslide over the same period. And we can clearly see the impact of the antecedent conditions here too. Following the historic drought between 2012 and 2015, we observed above average rainfall in water year 2016, but very little movement, still catching up from the lingering effects of that drought, followed by extraordinary rainfall and high movement in 2017, and subsequently slightly below average rainfall and below average movement in 2018. In 2019, total rainfall is high again, movement picks back up, and then after that, we have a series of low rainfall years leading to minimal movement. And these patterns demonstrate how the multi-year variability is really integrated into the long-term patterns of landslide movement as we see the effects of both drought and high rainfall propagating forward. So to put all that succinctly, memory matters in this system. Going back to our magic landslide formula, changes to both antecedent conditions and triggering rainfall are significant at Oak Ridge because the integrated effects of multi-year precipitation patterns are key to forecasting slow landslide movement. So based on our modeling, future increases in precipitation variability may lead to a decrease in movement for landslides like Oak Ridge, particularly in areas where recharge is precipitation limited. And this is true in part because increasing precipitation intensity may decrease landslide movement by diverting rainfall to runoff rather than recharge, and in part because although both wet and dry years are expected to become more frequent, the impact of the increasing wet years can't compensate for the more frequent drought due to the importance of antecedent saturation for dictating landslide movement. I'm putting that all together to summarize the pieces from both parts here. At Oak Ridge, our deep-seated, slow-moving landslide, we're anticipating a decrease in overall landslide movement due to the increased rainfall intensity and the decreased efficacy of wet years relative to dry years. At Balt 1, our proxy for a shallow, fast-moving translational slide, we anticipate an increase in the number of landslide days driven by an increase in rainfall intensity, which occurs despite a decrease in the average number of rainy days. And taken together, these results suggest that landscapes are going to be sensitive to different aspects of climate change, depending on the dominant landslide process in the area. And that's all I've got for now. Happy to take any questions.